And let me share my screen. Can you see my slides? Oh, perfect. Yeah, so welcome everybody. I'm Julian from the vulnerability research team, and today I would like to talk a bit about generic semantic version matching. So I would like to start with a bit of background. And by the way, if you have questions or comments or suggestions, just interrupt me. So it's nice if we can have some sort of discussion while we go through this. Yeah, so for semantic versioning, there's a specification, and semantic versioning is basically an approach that or a procedure that attaches version numbers to software. And the idea is that you have a unique version number that you assign to a software project, and that the state of the software project is represented by that number. And usually you have like three main components. That's called also version core in the Semver specification. That's major, minor, and patch. Usually it's expressed like this: v1.2.3. And in this example version, v1.2.3, it's the major component is 1, the minor component 2, and the patch component 3. So they are like separated by dots, and they have some meaning attached to them. So the major version is usually incremented when you apply a backwards incompatible change to your software. The minor version is incremented if you add new backwards compatible functionality to your software, and the patch version is usually for minor bug fixes that are all backwards compatible. And when you're looking into the Semver specification that I've linked in the actually the slides are available. So in the agenda, you can find a link to the slides too if you want to follow through and click on some of the links while you go through the slides. So this specification contains a grammar, and this grammar tells you exactly how a semantic version looks like and what the rules of semantic versioning are. So when to increment and when which part of the version to increment. And this is like an excerpt from the grammar. This is the top level rule, and it's basically saying that a valid semantic version consists of a version core, which is like these three items here, plus a suffix, which can be a pre-release suffix or a build suffix. Build suffixes are added with a plus, and pre-release suffixes with a minus. But for this like brown bag, we only consider these pre-release suffixes because the build suffix can be just dropped. It's just meta information that you're adding to the version, but it doesn't contain any information about how this version compares to other versions. And this is down below. You find the list of valid semantic versions according to the Semver specification. So this list here is basically all like valid semantic versions. So semantic versioning, so the Semver spec in particular is very clear about the structure of a semantic version and also how to use it, how to apply semantic versioning using semantic versions. But it's purposely simplistic. So it's like a document that you can read in an hour or two, and you would basically understand everything you need to know about semantic versioning. This is the biggest strength, but maybe also the biggest weakness, because this led a lot of languages, ecosystems, and package managers to define their own non-standard native extension of semantic versioning that is not really backwards compatible, so to say. So they support all of the stuff that you can use for semantic versioning, but they have a lot of stuff that they add on top, which is not compatible with the Semver specification. And the first part is, so the Semver specification is mostly about semantic versioning and how to compare semantic version strings, but it's not about semantic version matching. So when you're looking at package managers, for example, that you may use like a pip or gem, you usually can use something like version constraints, where you say that I would like to install a version that lies in this particular range. And this is something that the Semver specification does not really cover. And this is also the reason why when depending on which ecosystem you're on, when you're using Maven, pip, or Composer, they use different ways to express semantic version constraints. And this leads to the problem that the same versions are treated differently depending on the package type you're using. So to give you a small example, I've prepared a small example for that. So what I want to do is I would like to take a list of semantic versions, the same list basically, and I would like to sort them using the native semantic version library that pip is using and the native semantic version library that Maven is using. Just to show you the scripts that I'm using. Oops. So from Maven, I have like a small like Java class that's using a semantic version library that's part of Maven. That's called like default artifact version. And this gives you some semantic version matching capabilities that's compatible with Maven, the semantic version scheme that Maven is using. And as input, I will provide a JSON file, and this class here will basically go through this file and determine what semantic version is greater than the other, and we'll do some sorting and we'll print out the list of sorted versions. This is basically all happening here. So we're just invoking the native semantic version library. And then I will do the same for Python. So for Python, I also have like a small script that does the same thing. It's using packaging version that's also what pip is using. So the same Semver matcher that's integrated within pip, and we're using this just to parse a JSON file with semantic version, list of semantic version, and sort it and provide the sorted semantic version. So for that, I've prepared a small makefile, and it's basically just taking. You can see we invoke make all here, where we're invoking both tools, and it will just take the file and sort the list. And the list is just check simple JSON. Okay, this is the list of input versions that we would like to sort, and I will take this as input, and I will run the sorting. And as output, you can see the sorted semantic versions. So for Maven and PyPI, we have the same list because this here is just the version core. So this list here only contains semantic versions according to the version core, and there are no like pitfalls when you're just using those versions. But then I've prepared another list which is inconsistent JSON that is different. So it contains only two versions, and one of them is again a simple version core version, and the other one is a version that's specific to Maven. So Maven has the concept of an SP release, which is actually a post release. So it's supposed to be greater than 1, 2, 3. And when I'm invoking the same script with this as input, the sorting order is different. So for Maven, it considers this SP release to be greater than 1.2.3, and for PyPI, it's the other way around. So actually, PyPI doesn't even know what an SP release is. So it's actually it's basically an invalid version if you take the Semver specification. And this is one of the problems that you have when because I mean the standard of semantic version is kind of nice, but then these different package registries ecosystems, they use different flavors, and at a certain point it's hard to unify all of this to one common system, because they use some contextual knowledge about different version suffixes that other package registries ecosystems don't really know about. And so this was just the introduction, and then I wanted to talk about the motivation, why we wanted to have some generic semantic version matcher in the first place, why this is useful to us. So as in the vulnerability research team, we are basically curating the GitLab advisory database for dependency scanning. And this is a collection of essentially JSON files, and we integrate different data sources. So we have like NVD and Friends of PHP, RubySec, and we take these data sources and extract data from them, and then generate advisories in YAML format that are adhere to our own advisory format specification. And in the GitLab advisory database, we have different package types that are supported. So PyPI, NPM, Maven, Go, Packages, and Gem. These are the package types we currently support. And as I showed in the previous example, all of them, they do use different flavors of semantic versioning. They have different ways to express semantic versions, but also different ways to express the version constraints between those versions. But all of them at the same time have their own native Semver libraries. So when you're using PyPI, like a package manager, pip, or NPM, where you have like bundler, sorry, not bundler, yarn, or NPM, they actually use their own, or they have their own native semantic version library that's integrated into the package manager itself. And this is, they basically use their own library to implement all the quirks and special cases that they need for their use case. So for the, I just wanted to shortly introduce a snippet of the advisory format that we are using to motivate this a little bit better. So in our advisory format, we have a couple of fields that are related to versions. We have an affected range field, and this affected range field contains version ranges that say that this advisory is related to these versions of this particular package. So this is basically what this affected range is about. It tells you that this package is vulnerable starting from version 1.9 up to version 2.7.1, or that version 2.8 is vulnerable. Then we have fixed versions, and fixed versions is usually mutually exclusive with affected range. So these are versions that are not affected per definition, basically. And then we have not impacted. Oh, sorry, Mo, you were.
I have one question. Sorry to interrupt. Is that grammar that represents the affected range? Is that a grammar that we defined, or is this like a standard format for defining?
So this syntax here is package specific. So this is I listed all the standards or all the rules so that we are using down below. So this is expressed in terms of the language used by the target package type. So if you're using Maven, then this here would be like the Maven Semver syntax. If you're using Gem, this would be the Ruby constraint syntax, and so on. And I linked them below. So these are like the different specification and rules. I mean, for Python, it's even part of the language standard. So they have like a PEP rule that defines all the different constraints and rules for semantic version matching. But this part here is specific to the package type. So it looks different depending on which advisory this is used for. So this here, for example, is Python. This is a snippet or an excerpt from a Python advisory, or an advisory related to a Python package. And yeah, so what we needed was like a tool that helps us to generate these different syntaxes. So that was the first motivation to have our own generic semantic version library, because we wanted to be able to generate these range syntaxes depending on the target package type. Oh yeah, and this is like an example that shows you the different syntaxes for Gem, Maven. So for Ruby gems, you have this, basically it's like a disjunction of conjunctions. So you have a disjunction is expressed with two pipes, and then you have between these pipes, you have these version ranges. So this space is a logical end. So this here would be a range that goes from 2.00 up to 2.12.4. And this here would be another range that goes from 3.00 up to 4.00 beta 7. And these are like connected through a logical disjunction. So you would either match this one or that one, and depending on if you find an overlap, you would return true when you're going through the affected range. For Maven, they use a more mathematical notation where you have brackets. So ranges are, for ranges, you use these brackets for lower and upper bound, and disjunction is a comma between these segments. And for NPM, you have also pipes that denote logical disjunction, and spaces for conjunction. And yeah, so it's there's a lot of similarities, but just some minor differences between the different syntaxes that they're using. And the data, just to give you like a general idea how this data is used. So we have this data in the advisories, and then we have the gymnasium analyzers, and what they're doing is they download the YAML files or the advisories from the advisory database, and then they scan basically the source code. So let's assume you have like a Python project. What the Gymnasium analyzer does is he basically scans or parses the dependency file that contains or the log file that contains all of the versions that are used as dependencies, and cross-validates that with the information from the advisory database by trying to figure out, is there an advisory that relates to dependency X or Y? And then the Gymnasium analyzer basically takes the affected range and passes this information onto what we call a V-range tool. So at the moment, what we're doing in Gymnasium, or what the Gymnasium analyzer does, is for every single package type that we support, it implements a script in the native language, implemented in the native language that uses the native semantic version library to match those versions. So for Python, what would happen is that we have a V-range script written in Python that uses the native semantic version matching library, and Gymnasium passes on the affected range together with the information from the log file to the V-range tool to check the version for Python. The same for PHP and for other languages. So we kind of dispatch this to the tools that can cope with all the quirks of the native assembler libraries in the Gymnasium analyzer. Just wanted to add this to basically give you the context in which this data is being used and how it's being used at the moment. So the first motivation was about generating the affected range in terms of the different like target syntaxes, type syntaxes that we support. And another goal that we had was we wanted to leverage redundancies that we have in the advisories. So to give you an example, affected range and fixed versions are correlated. So if you know affected range, you can basically infer fixed versions, because from affected range, you can compute the non-affected range. And if you know the non-affected range, you can basically collect information from the package registry to see what versions have been released that fall into the non-affected range. And those are the fixed versions. For not impacted, it's the same. So not impacted and affected range is kind of connected. So this not impacted field, by the way, is only a textual description that we use to tell the user what are the versions that are not impacted, so it's visible or readable by the user. And for that, we can just invert the affected range and generate a textual description from the inverted range. And solution can be inferred from fixed versions, so we can generate the solution from the fixed versions, basically. And the third motivation was that's more like MVD related, because I would say NVD is our most important data source from which we extract advisories on a daily basis. And one of the issues that we had with NVD is that sometimes when you scan through the feed, you encounter CVEs where version information is reported in a concrete way. So instead of version ranges, you will basically get a list of distinct versions, and we cannot just basically extract this and pass this into or put this into an advisory file, because it would blow up the advisories quite significantly. Instead, we would like to infer a range from this list. So in this case, so this is actually taken from a real example. You have like 4 versions, and as you can see, they're consecutive because the patch version is always incremented by 1. And in I would say 99.99% of the cases, this means that this is a version range. So this range spans from 2.2.0 up to 2.2.3. So instead of using like a list of versions, we can just collapse this into a version range and then use the range instead. And this is what we needed December library 2, because we for doing like this version collapsing, you need to have some knowledge about semantic versioning and know and whether or not 2 versions have an offset of 1 or not in order to collapse them. And the fourth motivation was about advisory validation. So for the GitLab advisory database is open, so we hope that in the future, more users will contribute to the advisory database, and we would like to automate the validation of advisories as much as possible. So find inconsistencies between affected and fixed versions is one of these validation tasks that we have implemented in a CI job for the GitLab advisory database. And the second part is since we have since I think 1 month we are now a CNA, and the vulnerability research team is also responsible for issuing CVE numbers. So and we can reuse the semantic version, generic semantic version library that we've developed also to find inconsistencies in version information that is attached to CVEs that are submitted through our CVE workflow. And yeah, so there's like a couple of motivations that we have to build a unified semantic version matching system. Yeah, this is just a summary of what I explained earlier. So first, we want to generate affected range based on the semantic version dialect for the target package type. We want to make use of these redundancies that we have in the advisories to automatically generate information as much as possible. Ability to collapse versions for NVD, and automating the validation as much as possible. So this is also the point where we kind of, I mean, we didn't really go through a requirements phase. It's more like I just was thinking about when we started, what we thought the requirements were when we developed the first version. So I provide this list which contains all the functionality that we wanted, semantic or generic semantic version matcher to support. So first we wanted to provide a unified interface to the language-specific SAMVER dialects. We want to match semantic versions in a language agnostic way. So we want to be independent from the package type or the ecosystem. We want to be able to collapse concrete versions. That was the NVD issue that I showed you earlier, and word ranges. The approach that we're using should be able to cope with scattered non-consecutive ranges. What I mean by that is that if you have a version constraints that spans multiple ranges, you want to match a version against all of them. So it's like having a disjunction of conjunctions where you have multiple version ranges, and you want to know does this version fit into one of them, and otherwise you cannot really realize. Or you cannot really implement a semantic version constraint matcher that's based on version constraints. And then last but not least, we wanted the matcher to match versions gracefully and handles the constraints in the best of effort manner. So it's like a smallest common denominator that's very stable, that can cope with the different dialects, and that is, from our perspective, an advantage. But generally speaking, this may be also a drawback, because when you're doing it like that, like this, when you implement a generic semantic version matcher in the smallest common denominator way, you're losing soundness and completeness. So I was talking about the vRange tools earlier that implement the semantic version matching according to the rules of the ecosystem or language, target language you're using. And you can consider them as a baseline. So because they do exactly what the people that are using the ecosystem want them to do. If you have like Python, for example, and you're looking at the PEP specification implementation of this native SAMVER matching library, does exactly what's specified in the specification. And if you implement a generic semantic version matcher, for this matcher to be sound and complete, it should behave exactly the same as all the native SAMVER matcher, but it never can. So this is like some goal that we can never achieve, because if we want to guarantee soundness and completeness, our matcher should behave exactly the same as a native SAMVER library. It should fail in the same situations. It should match gracefully in the same situations. So which basically means we have to re-implement the native matching algorithm, which we don't want to do. So this is like a trade-off. In our context, we can make the sacrifice. We don't need soundness and completeness because we have control over the input data. So we can make assumptions about the input data that we're getting, and we have some knowledge about the input data. But you cannot really use this as a replacement for every single native version matcher because there will be always differences in the way it behaves. It matches versions. When you take, because in the earlier example, I showed you the difference between PyPI and Maven. And if you think about implementing a generic version matcher that can cope with the SP releases like Maven, then it basically knows what SP releases are, and then it already doesn't behave anymore like PyPI, which doesn't know anything about SP releases. So this is something that that is unavoidable, but this is the trade-off that we I think that's good in our context, at least that we can cope with in our context. Okay, so this was like just a disclaimer, and now I wanted to show you some of the tools that you could use with the Semver dialects library. That's so we have developed a small gem that you could use, and the source code is also available. I think I linked it in the agenda, so you could play with it and look at the implementation, the test cases that we implemented there. And I just wanted to walk you through some of the features. So first, we have a semantic version representation. So we've implemented, tried to come up with a generic semantic version representation based on the version core and the suffix. So generally speaking, semantic version just consists of the version core, which is major, minor, and patch release, plus the pre-release suffix. This is basically how we implement it. So when you're looking at the examples, I have some Ruby code here, where you're creating a new semantic version. So this is also the interface of Semver dialects of the Ruby gem. We creating a new version 1.2.3, and it will divide this version into 3 segments. Here you can see these 3 segments divided by columns, 1, 2, 3, and you can ask for the major, minor, and patch version in this semantic version string. Then the second part is about how to, if you have like 2 semantic versions, how you can compare them to one another. And for that, we've basically using a very generic representation that eliminates all the trailing zeros. So this is one step that we're doing when you, for example, compare 2 versions like 2.00 and 2.0, they're the same. And what you can do is you can just eliminate the trailing zeros. Which we have to do because we cannot assume that all the versions that you are providing to the version matcher are actually valid semantic versions. Because a valid semantic version would mean that you have like 3 segments, but basically all native Semver checkers that we've integrated or that we know of, they always can also can cope with versions that don't adhere to this like 3 segment standard, where you only have maybe 1 version number or the first 2 version segments. And this is the reason why we representing the versions in a way that we eliminate all the trailing zeros. We only keep the non-zero prefix. And so in this example, by eliminating the zeros for S2, so you can see we're creating 2 semantic versions, 2, and as S1 is 2 and S2 is 2.00. And by eliminating the trailing zero, we ensure that both of these versions are actually the same. So they compare, and when you're comparing them with the quality, this will be basically true. And then the next part is about dealing with these language-specific suffixes that you may encounter when you use, for example, Maven, or generally speaking, these pre-release suffixes, they have to be translated to something that can be compared. And what we're doing is we take these version suffixes and we translate them into the numeric domain. And we can safely do this because for the Semver specification, it doesn't know about negative integers or negative numbers in general. It only is concerned about positive numbers. So if you have, for example, like a release candidate, usually a release candidate is smaller than the actual release. So this version here, like 2.00 RC1, is smaller than 2.00, which is a full release basically. And what we're doing is we replace RC, or we map RC to a numeric value, which is -11 in this case. So I think we have now overall about a dozen of different mappings that are commonly used for the different package types. And RC is mapped to this number. And for what we're doing then is we essentially use these different segments and compare them one by another. I will show an example shortly. So this here is like, here we're creating like 4 different semantic versions: 2.0 RC1, 2.0 RC2, 2.0 release, and final. And this is the corresponding output. And you can see that we have like these 3 segments. So RC is translated to -11 for both of them. But we keep the suffix. So RC1 is -11.1 and RC2 is -11.2, because this version here, like RC2, is greater than RC1. So we have to keep the trailing number for the release candidate. And then we, in these 5 commands, we're basically comparing the different semantic versions with one another. So here we compare 2.0 release with the other release, and it's the same, so it deals true. Here we compare release with final, it's also the same. So for Maven, a release is the same as a final version. And then we check whether the final is greater than RC1, which is also true because it's just a release candidate. And the same here. And for release and smaller final, this is false because release and final are basically the same. And this is the way how we make these language specific suffixes or the release information comparable. We just remap them into the numeric domain so that we can actually compare them. And the comparison itself works like this. So if you have like a constraint or a version check where you would like to know, is version 2.00 greater than 2.00 RC1? The first thing that I've mentioned earlier is we just eliminate all the trailing zeros because they're just redundant. We don't actually need them. So this version 2.00 would translate to 2, and 2.00 RC1 would translate to RC1. In the next step, we would basically remap these language-specific suffixes to numbers. So RC is translated into -11. We keep the 1 because it's this is still important for comparison. And because this version here has now 3 segments, we equalize the length for both versions that we want to compare. So we add 2 trailing zeros to this 2 to make to ensure that both of the version segments or version numbers have the same length, so that we can just iterate through the segments and compare them. And that's what the next thing that we are doing is we iterate over every single segment. So we would start with these 2 segments. These are like the first 2, like 2. So we would compare this 2 with this 2. And since they are equal, we go on and check the next segment. And the next segment would be 0 and -11. And 0 is greater than -11. So we can already stop here because so the constraint or the version check would be satisfied as we were looking for, or we wanted to know whether this version is greater than that version, which is true. So we can stop when we check the second segment, essentially. So basically what we're doing is we take these semantic versions, we divide it into segments, and then we iterate over the segments and compare them numerically. And that's basically the way how we implement semantic version comparison. But that is, oh, are there any like questions or concerns, or did I explain something not well?
This is fantastic. I just quickly went through the README, and it says that you can install this gem, some Verdilex from Ruby Gems, but I don't see it published there yet. Is that going to be published to Ruby Gems?
Yeah, we want to publish this at Ruby Gems. At the moment, you can install it through Git though. So I think in the repository I've added a gem file that contains the Git hash, so you can just add this to your to the gem file and it should work. So you could play with.
Yeah, I'd love to just add it as a dependency on my gem spec without having to specify Git. So if it does end up on Ruby gems, please let me know.
Yeah. Yeah. So the first part was about the structure of a semantic version and how to compare two semantic versions. But then we also want to be able to express semantic version constraints. And this is where we can use linear interval arithmetic, which is quite useful because it's very generic. So we can do everything we want with linear interval arithmetic because it treats intervals as sets. So we can use all the standard set operations to solve version constraints. And just as a to give a little bit of background, so for linear interval arithmetic, we have different types of intervals. I just abbreviated left and right with L and R, and A and B are lower and upper bounds. So these are like the lower and upper bounds for the different numeric ranges that we have. Usually, sometimes I also call them just cuts or version cuts. So I use this interchangeably. So in linear interval arithmetic, you can have different types of intervals, and the first type is left-right closed. So this is an interval that's left-right closed, and you have a lower bound of A and an upper bound of B. And what this range basically says is that it covers all the numbers that are greater or equals than 2 and or smaller and equals and smaller and equals than B. Then we have like left open and right closed intervals, which means that all the values are covered that are greater than A. So A is not included, basically, and smaller equals B. Then you have left closed and right open intervals where you say that this is like greater equals A and smaller B, and left right open, which is greater A and smaller B. And then you also have unbounded intervals, which is like minus infinity and plus infinity. So this is for smaller or smaller equals or greater equals constraints. You would use these sort of intervals to express them. And for sample dialects, we implemented or the generic representation we use to express version constraints is just numeric intervals. That's basically the representation we are using. And as a small utility, we have created a version parser that takes our unified like syntax that we are using and generates an interval from that. So for example, this here, this first statement you can see here creates an interval that's greater equals 1 and smaller equals 2. So this is an left right closed interval, and you can see the output here. So this is like 1 2. For the second one, it would create a left open right closed interval, and the third one creates a left closed right open interval, and you can see the outputs here down below. So this is the representation we use for constraints, version constraints. We'll provide more examples on the next slides about that. So the reason why we use linear interval arithmetic is that you can, as I mentioned earlier, intervals are just sets, and you can use set operations. So you can use union, intersection, and complement, and which is basically all you need to do semantic version matching. The first operation that's important to us is like intersection, and intersection is important to us because you can use this to check whether a version lies within a certain range or not. So let's suppose you have your affected range from the advisory that I showed earlier, which gives you like a set of ranges, and then you would like to know whether a version falls into this affected range, and you can do this by intersection. An intersection is defined like this. So you have like first we have like ranges. I defined them like this. So you have a lower bound, which is so first you have two intervals x and y, and for every interval you have a lower and upper bound. So lower bound would be xl, and upper bound would be xu for x, and for y a lower bound would be yl and yu for upper bound. And if you want to compute the intersection for x and y, you can generate a new interval by applying this recipe where you take the maximum of xl and yl, the minimum of xu and yu, and you have your intersection, basically, if x and y have points in common. If they don't have points in common, then the intersection is just the empty set. So to give it a concrete example, if you have 2 and 5 and 3 and 10, just for simplicity, I'm using just normal integers, no semantic versions in this case. If you intersect them, this would yield like 3 and 5, because 3 and 5 are the numbers that appear in both of these ranges. So this is like the intersection for 2, 5, 3, 10. If you want to intersect 2 and 5 and 7 and 10, this is not possible because there's no overlap between these two ranges. So this would just yield the empty set. And this is something that we implemented as part of our interval representation. So again, I have some like a Ruby code that just creates like a range 2 to 5. So this is like the same examples that we see here, and intersects it with 310, which is basically this example. So the first line here corresponds to this example, and the second line here corresponds to that example. And you can see that the output is exactly the same as here in this example. So this is the use case again for why we need intersection is that we just have to be able to check whether a version that's part of a dependency file falls into the affected range that is contained in the advisory, now advisory.
I may have missed this, Julian, but should that not be 3, 4, 5?
What I usually here it's that the 4 is implicitly contained, because this is like
because we're still representing in this. Okay, sorry.
Yeah.
It's the min-max as.
Yeah, exactly.
It's not an array. It's the same. Okay.
That's a good point, because here the lower bound and the upper bound, this basically means that they're only covering the frame of your range, and here it would be like 3, 4, 5. Yeah, and here this basically means 7, 8, 9, and 10. Yeah.
So the output is actually the same grammar that was used to define the input, and I interpreted that as an array of versions, but it's the grammar. Yeah. Okay.
Yeah. Sorry. Sorry for this notation. That's true. I should have used a different notation for that. Yeah. And the next part is about union. So union is the other important operation that we need. And for the union operation, it's there's also a recipe. So if you have x and y, in order to build the union, you just can take the minimum of xl, yl, and the maximum of xu, yu as this is the upper bound, and that's the lower bound. And then you have your union if x and y have points in common. If they don't have points in common, like in the second example here, then you create something that's called, I think, disjoint union, where you have like a range of intervals basically, and that's basically how we implement it. And this is interesting for matching affected ranges, because what this means is basically you have here ranges and which are connected through an implicit disjunction, so you can just iterate through it and then and check the versions against this range. And this is some Ruby code that's using the code that corresponds to this example. Again, here we have like 2 and 5 and 3 and 10. So this is this example. This corresponds to this line, and the union is 2 to 10. So this lower bound and upper bound. This is like corresponds to this example here. And then we have a version range that is something that we use to organize intervals. So that's touching on the second example here, where we have a range of intervals, and here we create the version range first, and then we are adding the different versions to this interval. And the nice thing about that is we can match the different versions that are part of this version range. And one functionality that we implemented here is the collapsing operation, where you can take two versions. Like here we have 2.5 and 3.10, and for this is the output that corresponds to this line here, which shows you the every single item that's part of this version range. But if you want to collapse them, you can just invoke collapse, and then both of them will be merged together because they have an overlap. So you can just use basically this single range to express the same thing. And yeah, this second example corresponds to this line, where we have two ranges that don't overlap. And this basically means that we will have a version range that contains two different version like intervals, version intervals. Yeah. Okay. So,
This
oh,
is
sorry.
amazing, Julian. If I'm understanding this correctly, this can be used outside of just affected version. For example, if I wanted to say, take a gem spec where I've got different constraints represented in the Ruby syntax, I could then convert those into this intermediate grammar. And from the grammar, I could actually resolve the gemfile the equivalent of the gemfile.lock. That's the space that we're starting to approach with these tools, right?
Yeah, that's true. That's possible because all of these special operations like this pessimistic operator or the tilde or the caret.
Yes, for all the
They
different package
can,
managers can be represented
yeah,
in this intermediate grammar.
Yeah, they can be all translated to intervals basically, or to a set of intervals. Yeah.
This is exciting, Julian.
Yeah, the only thing that is a bit tricky is this .x thing. So sometimes you find this weird
Yeah, .NET seems to have a lot of packages with that extra.
Yeah. But
I forget what that was called, the beta version, or you described it in the first slide, and I forget the technical term for that.
oh, yeah, there was like this pre-release information, or post-release information, and a build information that's attached to the before the build information. This is what we are doing at the moment. We just drop it because we don't
know how to interpret.
Don't really think it's relevant for comparing, at least. So we just eliminate this part because it's usually just used to attach meta information to the version itself that it's not really related to, I think, semantic version comparison or semantic version matching. Yeah. And the last piece is about union and intersection used together. As I mentioned earlier, we need to be able to have like a disjunction of conjunctions, so like a version range that contains multiple intervals. And we want to be able to collapse versions, especially in the context of NVD, where we take fetch data from NVD. And in this example, we create a version range and we add several intervals, like the interval which is going from 2.1.2 to 5.1.2, and the other interval that's going from 3.1 to 10. And then in the first command here, we check whether R1 overlaps with a version interval that's greater equal 0 or smaller 2.1, which is not the case because they're like disjunctive, so there's no overlap, so it returns false. And in the second example, we try to figure out whether the version 5.5, so this here is like a concrete, basically a single version that we would like to check. Could also, in our syntax, you could also just use equals 5.5, which translates to this interval, whether this lies in this version range, and the result is true in this case. Oh yeah, and the union part is basically here. This is the first part here where you're adding version. This is about union, unifying them, adding them to the version range. And the second part here, overlapping, checking the overlap, is about intersection, where we use intersection to check whether a version falls into this version range. And the last operation that's relevant to us is the complement operation. And complement is usually used to get the set difference between two intervals. So this is, yeah, maybe this is not, this code snippet or fragment here is not really easy to understand. It's a bit bloated, but the example may be better. If you take like 3.5 and we want to diff it or to create a complement between 3.5 and 1.3, what we do is we eliminate all the versions that the first interval and the second interval have in common, and this would yield like 4, 5, because both of them have like 3 in common. And what we're doing is we are eliminating the 3 from the first interval, which would yield 4, 5. And the same is also true for the other one. So this is just some examples how the complement is used. And this is the relative complement. So if you have like 2 intervals, you can create a relative complement. But for us, the relative complement is not really that important. We just need it to compute the total complement, which is like defined here. If you take the like total complement, I just should call it complement, but I call it total because it's it better maybe better to understand because this is like relative. I would just call it total complement. You can just create the complement between the like universal range that's basically matching the whole universe, which is like minus infinity to plus infinity minus the range you're interested in. And the cool thing about that is that you can, if you have like a concrete version, let's say of 1, 3, which is like this version range that we have in this example here, and you create a complement, then you're matching all the versions that are not in the actual version, and that's very useful if you want to invert the affected range. So if you have the affected range, you create a complement, you get the non-affected range, and then you can use this to infer a fixed version and these sort of things. And this is an example here where we're using Zenver dialects to, this is basically the example that corresponds to the second line. Here we have like a range that's going from 1 to 3, and we invert it where we get the range from minus infinity to 1. And note that this is exclusive, so this is actually going to 0 instead of, so because this is like 1 is excluded, and this is starting from 4 going to plus infinity. And the same for the second example. Oh,
be up to 0.9 repeating, not including 1.
Yeah. So this
okay.
is
so then okay. 0.1 would be everything almost up to 0. Okay, sorry.
yeah. This is because we support for the Zenver dialects, we support all the different kinds of intervals that we saw at the beginning. And in this case, we just write it like this, but this here is actually, you could translate it into a closed interval too by basically incrementing or decrementing 1. Yeah, if you decrement 1.
My bad. Yeah, I was thinking in terms of floats, but it doesn't apply here because we've already we've taken the 3 segments of the Zenver, and they're just going to be integers at that point.
Yeah, that's true. So we basically just have segments of integers. So we don't have, it's all like discrete, and we don't have like floating point numbers.
Much
so
simpler.
This is the use case is that you take that's affected range use case. Essentially, you take the affected range and complement it to get the non-affected range. And that was the point that you mentioned earlier, Mo, is that you can translate these special operators into intervals, basically. So the caret operator could be, if you have a version, could be translated to this range. Tilde could be translated into this range, and the pessimistic operator, I think that's how they call it, could be translated into that into this range. I think this is NPM, and that's equivalent for Gem, for Ruby gems. Yeah.
So what I'm going to do, Julian, is I'm going to go take a pom.xml, parse out the dependency versions in there, try to convert the Maven description of those dependencies into the interval syntax, and then from there see if we can resolve what would effectively be the runtime dependencies from that, just the declared dependencies. Because if we could do that, and do that in a way that's deterministic, we can save having to install Maven and other tools to actually do the resolution. But there's still the issue of what you described of the dash beta and all the other suffixes and interpreting them.
What unfortunately with the gem that was the soundness and completeness issue that we had or that I mentioned earlier, is that we cannot guarantee that it behaves exactly the same as the native package manager would, or semantic version library that's used in this package manager would do. Because to guarantee that, we would have to re-implement the, basically we have to re-implement the semantic version match that they're using, which is, I think for Maven, because I think Maven is one of the big outliers there, because they use so many different non-standard suffixes. For the other ones, it may be a bit easier, but for Maven, it's Maven is like a bit special there. It's not even valid semantic versioning what they are doing, because they just use a dot and then they put the suffix after that. Yeah.
So Julian, maybe you could be the champion of just sharing the knowledge on this interval grammar, so that all the different package managers can start adopting a shared standard for describing constraints, and therefore don't have to re-implement their own way for satisfying our constraint resolution. One day, right? Sorry, I'm interrupting.
I'm not sure if I can take this on. It would be like a large undertaking, I suppose. It's because every package manager has so different ways of dealing with that. I think sometimes it's part of the language standard. So I think Python that's kind of great, because they have like a standard document that you can look up, and you exactly know how the versions are matched, and you could actually re-implement it in the same way. But it's not as well documented for example, PHP. For Composer, there it's not really part, I think, of the language standard. It's just the way how Composer most probably does it. I'm not even sure if there's like a standard PHP way of dealing with semantic versions, and this makes things sometimes a bit tricky. And for Maven, it's because Maven itself is also specific to the ecosystem. That I think most of the tools that are part of the Maven ecosystem, they adhere to the Maven. It's not really a specification, but the Maven way of dealing with semantic versions. But yeah. Oh yeah, that's so the last part is about the coping with the different semantic version constraint syntaxes. So what I've just mostly described up to this point was how we represent semantic versions, and how do we what our generic approach is to match them by means of linear interval arithmetic. But we also have to be able to process the different version constraint strings ourselves. So we have to be able to parse them and to translate them into our generic representation. So therefore, we've implemented like parsers for all the package types that we, like small parsers for all the package types that we support. So packages, Maven, Go. We basically have like a version translator class that you can see here. And for this class, we use a function called translate packages or translate Maven, which takes a string that's specific to the target package type and translates this into our generic representation. And then we could basically take this generic representation and create intervals from that, so that we can compare and compute them. So this is just an example where we take these two constraints are essentially the same, just expressed in different dialects. So the first one is expressed in the packages dialect, and the second one is expressed in the Maven dialect, and then we translate them, and we end up with the same, basically the same output, which is our representation that we are using. And yeah, then there's just some like a fun slide basically about how we generate textual descriptions from versions. So if we have like a version interval, we can also directly just generate textual descriptions that provides a text, basically natural text that describes the version range. So to give an example here, in this case, we take a version range. We again add a couple of intervals to this version range, and the first code line.
This is just showing off now, Julian. This is just showing.
Yeah, this was the fun part. This writing the natural text output. That we actually use this for the advisory generation part because we want this text to be consistent across all the advisories. So the first line translates this version interval to the gem constraint. The second one to the Maven constraint, and then this here is the natural like description text that you see in the advisory. And this is just the same for the inverted version interval, which is basically these two lines here. Is the text.
Now let's add I18N. Joking. Well, not joking. Actually, that's the next step for making multilingual support.
Yeah, that's true. But we don't have this yet for the advisory database, at least. Yeah, and that was basically everything that I had about the Semver dialects gem. But would be great if you like have some feedback, or I didn't even check in the agenda. Maybe some. Oh no, there's agenda is empty, I think. Yeah.
This was amazing, Julian. I'm just going to toss some feedback at you. Like the Semver dialect gem, looks like it's got some helper methods and utilities. It doesn't seem to follow some of the idioms for Ruby gem in terms of like name spacing underneath the gem name itself. And the README has a link to go install the gem from Ruby gems, which we can fix. These are all solvable problems, but it.
That's a good point. Actually, I've been using TTY which provided all
generate
of these
the commands. I saw that.
and I didn't like fill in all the gaps yet, so it's still VIP as a work in progress. WIP, sorry. Yeah, that's something we have to finish, I think, to be able to publish it on Ruby gems. But we already use it for advisory generation, and we also integrated it into the CI job for the GitLab advisory database to verify whether there are inconsistencies or something between affected and fixed versions, this sort of thing.
Awesome. Thank you so much. I really enjoyed listening and learning more about how you're doing this. So.
Thanks, Julian. This was great.
Thank you very much. I think then I can, if there like no further question, I think I can stop the recording.
I have one question, but I don't know. I can ask you offline. There was a slide where you listed the affected version, and then I think the candidate versions, like explicitly declared each of the versions that fall into the affected versions. Are you keeping that list up to date based on published versions for that package manager? Because as new versions are published, do you have to re-up? Sorry.
So the way how we do it at the moment is we for every advisory we generate, we keep the publication date and the date on which the advisory was last modified. So if there's an NVD update, we update the advisory, and which is triggered only by a new advisory that's published by NVD, and then we also fetch the new version information from the package registry itself. But it's triggered still by an update on the NVD side. So we don't really keep all the versions up to date all the time. We just wait for NVD to trigger basically, there's an updated advisory, and then we take the new version information if there's any from the package registry.
So that finite list can actually get stale because as new versions are published that fall into that range, it doesn't necessarily trigger an update to the advisory, which won't capture the latest versions.
If NVD doesn't update the advisory or the affected versions that are listed, then we wouldn't be able to capture this. That's true. So we're basically dependent on updates that are made on the data sources that we use. But for
the point-in-time capture.
Yeah. That's basically all based on the timestamps that we attach to the advisories, and then for every advisory sync, so we do it on a daily basis with NVD, for example. We check whether there's has been a change. So we basically compare timestamps, and then we fetch newly available data from NVD, but also from the package registry, which is mostly related to fixed version information.
Cool. So if there was a way to actually capture like new packages that are released that have a version that fall into that range, we could include that into that fixed list. Otherwise,
yeah. So the general approach, how we do it at the moment, is we take the first known version. So if you have like the non-affected range, so we take the affected range, then we invert it so that we get the non-affected range, and then we check for the first available version, so the smallest available version inside the non-affected range. So
and then start collecting those.
Yeah. So
until you reach the max.
It would give you like sort of a starting point. So you could say that this is the first fixed version that we know about, and everything that comes after that is okay. This is basically the implicit assumption that we make for the advisories.
That makes more sense. Then you don't have to keep that list up to date. And when we're determining if the version is vulnerable, we would just have to look at the minimum and the maximum to see if it falls into that range, rather than trying to keep the database up to date with every range or every version. Sorry, I'm talking out loud. Yeah, thinking out loud here.
Yeah. So I think we also generated in the description text. So when we have a fixed version, so which is always the smallest release inside the non-affected
range
version that we have, non-affected range, we always say that please upgrade as a solution field. We basically always say please upgrade to version X, Y, or later. We're saying that okay, everything after these versions is okay, so you can just upgrade to those. This is like the sort of workaround that we're using for this kind of situation.
That's fine.
Yeah.
I love what you're doing, Julian. This is great. I've learned so much, just like in terms of taking something like semantic versioning and breaking it down into its segments, describing them, the constraints, the way they can be represented, and then represent them in I forget, interval in the interval grammar. Is that the right term?
Yeah, so the semantic versions are represented as segments, basically. So every segment contains only, it's more or less like having an array of integers, basically. And because we want to compare them numerically, and then the version constraints are represented as in terms of linear intervals. That's
linear intervals.
Because that was like the most generic way to solve these kind of constraints. I mean, I think similar stuff is used also in constraint solving for domain pruning. So if you use a constraint solver that solves integer constraints, usually they also do some sort of domain pruning upfront, where they try to eliminate parts of the search space that are not really required. So if you have like x, like a symbolic variable x smaller than 5, you can already prune a lot of the search space upfront. So you don't have to assume the whole integer domain to be valid. You can just prune part of the search space. And I think they're using a similar stuff there to make the search space smaller.
Smaller.
Yeah, to prune parts of the search space.
Thanks, Julian.
Thank you so much.
It was fun. Thank you very much for joining. I forgot to stop recording.